Hi, today I will be discussing my final project for ENME489Y. The objective for this project was to create a 3D scan of an object on the University of Maryland's campus using a custom-built Lidar scanner. This was to learn about the different remote sensing technologies and to map an object using low-cost materials. Before we get into that, let's discuss what Lidar is. Lidar is a remote sensing technique, which basically just means that it collects information about the environment without contact. Lidar is an acronym, light detection and ranging. It is similar to radar systems, except Lidar systems use light wavelengths, which are on the order of nanometers, rather than radio waves, which are centimeters. This allows for much higher resolution in returns because you have a smaller diffraction limit. Lidar is an active system, which means that it sends something out, in this case photons from the laser, in order to collect information, like distance to the object. This allows us to create a 3D point cloud of distances from the scanner to create a point cloud of an object. For my Lidar sensor, I decided to use the class-provided two-part model of the Lidar mount to simplify the debugging process. The two-part model was chosen because of the 3D printing resources I had available. The sensor itself consists of three main components, not including the Pi. The transmitter, a red line laser approximately 700 nanometers in wavelength, will emit photons to be reflected off the target and captured by the receiver. The receiver, a Raspberry Pi camera, is originally mounted 12 inches away and positioned in parallel with the line laser. The distance to the object will be calculated using a triangulation method. For this method to work, the laser emits photons which reflect off the target. The camera receiver will detect those photons. Theta is determined by calculating the number of pixels the laser is away from the center of the image, multiplying by the radians per pixel, and then adding a radiant offset to compensate for the alignment errors. Using the known 12-inch distance between the transmitting laser and receiver, and some basic trigonometry, the distance can be approximated as the 12-inch separation distance divided by the tangent of the theta. Practically, as you increase the distance to the object, the pixel distance to the center decreases. The radians per pixel and radiant offset are experimentally determined through initial calibration. The calibration was first conducted as a proof of concept using a point laser and a Pi camera taped to a book 12 inches apart. The setup was placed in a fixed location and 6-inch markings were labeled on the floor for 10 feet in front of the laser. A book was held at each location while a picture was taken. At each location, I used computer vision principles to locate the laser dot. Taking the image on the left, I applied an HSV threshold to set the laser pixels high and everything else low. I then ran a contour finding algorithm to identify the centroid of the laser in the image. Using the centroid coordinate, I found the pixel distance to the center. This was repeated for the line laser by taking the vertically centered pixel at the calibration point. After calculating the pixel distance to the center for each of the 6-inch increments, I plotted distance versus pixel from center and adjusted a theoretical triangulation equation to match my data. This was for the point laser configuration. I then repeated the calibration steps for the line laser configuration, and from here on, I used the line laser theoretical curve to obtain my distance values. To ensure my scanner worked correctly, I placed a box in front of a wall, ran a scan, and then plotted the point cloud data. From that point cloud data, I verified that the box was flat in the image and that it was positioned a couple feet from the wall. This proved that my data was correct and that I can start scanning an object on campus. For my object, I chose the bird on the University of Maryland's campus near Ludwig Field. This is because it has distinguishable geometry in that there are both smooth features to identify the shape and subtle details to compare resolution. It has both regions of good reflectivity and dark regions to assess the reliability of the sensor. Lastly, the location had favorable lighting for the sensor and was a good medium-sized target approximately 5 feet tall. The unique capability of my Lidar sensor is that it scans from left to right as opposed to up and down, measuring each angle with a compass. This was to reduce the moment arm of the vertically positioned mount by rotating it on its side, which also reduced the effect of wind, and to mount an external display to make the system stand alone so I was not reliant on Wi-Fi or other systems. During collection, I positioned the scanner a couple feet from the object, powered on the laser and Pi, and then stopped at each angle in 1-degree increments. and captured an image from the pie. I noticed a couple of limitations where I had to stop and wait for cars and police to pass before continuing the scan due to noise considerations in the data. This scanner could also only be used at night and had trouble with the dark areas on the bird due to noise and scattering coefficient of the target. On a good scan with very few interruptions, it took approximately 30 minutes. I took 8 approximately equally spaced scans around the bird to ensure significant overlap and to ensure that if a scan did not turn out as hoped, it could be thrown out. The main challenges I ran into were environmental, including bright lights from the nearby stadium, and road, traffic, sunset, and police stops. While the police did not question me, they were present each night, sometimes for over an hour, with their lights on. In all of these cases, I just waited until they were gone. From my scans, I obtained an image as shown in the upper right. I then in some cases manually blocked out some troublesome areas that the HSV filter might not be able to remove by placing black shapes over the affected regions. I then ran a Python algorithm that applied an HSV threshold, then isolated each row, finding the laser light contour, identifying the centroid, calculating the distance to the center, and then matching it to the calibration curve to find the distance to the target. Using the distance to the target values for each row of pixels and the compass reading from the image, I calculated the XYZ coordinates using trigonometry and saved them into a text file. I repeated this process for all images at each viewpoint, saving a new text file for the different viewpoints. I then imported these XYZ coordinates into a mesh manipulation software called Cloud Compare. You can see that the front face of the bird turned out pretty well and has very little noise. Importing other scans, you can manually scale, translate, and rotate one point cloud to align it with another. Repeating this for the 4 viewpoints that had good results yields a complete point cloud of your object. My point cloud can be seen here. As you can see, some extraneous points are present and can be filtered out with segmentation. After filtering, I overlaid my point cloud onto a similar viewed picture of my object. You can see that the geometry matches pretty well to the original. You can see the beak in the correct place, the back, wing, neck, and body curvatures. I did have a slight alignment issue with one scan, which is why the belly of the point cloud does not exactly match the original object, but overall it matched pretty well. Returning to Cloud Compare, after computing normals on the point cloud, I ran a Poisson surface reconstruction to generate a mesh. The mesh is shown here. After exporting the mesh as an STL file, you can import it into other software to clean it up or get a better view. You can see the holes in the mesh from a low point cloud density, especially in the horizontal direction. As I scan left to right, the vertical dimension has a high density of points, leading to clearer features in the mesh. Importing the mesh into Autodesk NetFab, you can do other post-processing work to eliminate the holes through mesh refinement, but doing so tends to also remove some of the geometry. After finishing the post-processing, the purple on the left is the mesh vertices. The mesh did gain a couple of extraneous surfaces, which is why the neck area is expanded with the dark blob. But if you look at the mesh vertices, the geometry closely resembles the original object shown on the right. Overall, I was able to accomplish the goals of this project to scan a medium-sized object on campus and learn a lot about remote sensing and computer vision in the process. Thank you for watching.